Good evening, everybody. This is Ralph Chu, President of the Royal Astronomical Society of Canada, Toronto Centre. Welcome to our RASC Toronto Centre online session tonight. We apologize for the late start, but we've been tackling some major technology problems, but they look like they've all been solved, so here we are. Welcome again. We have a really great talk lined up for you, and without any further ado, I'm going to call on Paul Delaney to introduce our speaker.
Good evening, everybody. Thank you very much, Ralph. Yes, always a challenge when you're dealing with technology, and in this day and age, we're all having to become quite expert at it. At any rate, you are with us now, and we've got a terrific evening lined up for you. It's my distinct pleasure to actually introduce our speaker tonight, as I always do. It's my colleague from York University, Professor Michael de Robertis. Quick summary of where Michael has been: collected his master's degree out of Queen's University in '79, and then he came across to the western side of the country, joined me at the University of Victoria, completed his PhD there in 1983, stayed on the west coast, popped on down to Lick Observatory for a couple of years before heading back east, joining York University in 1985, and fair's fair, I followed him, and in 1986 we were reunited. We've been at York ever since. Michael was also the president of the Canadian Astronomical Society from 1998 to 2000. His specialties: M-dwarf stars, quasars, you name it, he likes it with respect to astronomy, and of course in more recent years has been very, very interested in the educational aspects of disseminating astronomy and astronomical inquiry to not only our undergraduate students but to people in general. And that of course brings us here tonight to a topic which he's become quite interested in over the last few years. Is there intelligent life beyond Earth? Michael.
Thank you very much, Paul, and to the Toronto Centre for the RASC for inviting me to give this talk. I've been asked to let everyone know that because of this clear format, questions will be entertained at the end and not throughout the session. I hope you'll understand. I prefer questions throughout, but technology doesn't permit. I would also like to say that whereas I've been a number of places on this Earth, I haven't been beyond Earth, and that's the subject of my talk this evening. We are all preoccupied, and understandably so, with the microscopic in our day-to-day lives and isolation and social distancing. But I'd like us now to think about, more sublime thoughts about whether there's intelligent life beyond Earth. And notice I've put intelligent life. Often talks of this nature just talk about life beyond Earth, but let's face it, I think you and I would agree over a glass of wine, or nothing at all, that it's better if we're talking about intelligent life. It's life. I'd like to play chess, or I'd like to play tennis with the life that we're going to discover at some point, not just merely intellectual curiosity. So clearly, one of humankind's most persistent and profound questions has been, of course, and continues to be, are we alone? Is there intelligent life in the universe out there? And that topic really has been one of significant interest throughout recorded history. I mean, you can go back even before the ancient Greeks, and people were, of course, interested in this subject, as were the ancient Greeks, and all the way through the Middle Ages. And of course, particularly since about 1950, when we as a species have become what they call technologically intelligent, which will play a role later on in this talk. Now, I have a disclaimer. I've often given a skeptical type talk about UFOs and ufology, but if the UFO phenomenon provides good evidence for the existence of extraterrestrial life, extraterrestrial intelligence, ETI as I'll abbreviate it here on, then we're done. We don't have to go any further, and we've answered the question. But I will assume that it does not provide good evidence. So, in order to answer, is anyone out there? That is there extraterrestrial intelligence? We're going to go on a systematic journey. This is one you might be somewhat familiar with. I have some interesting detours, I hope, that we'll encounter along the way. And I have some results from a very interesting study just done in the previous year by an Oxford group. And I'll leave that to the end, where they address this very question quantitatively. So we're going to break up the talk to 6 parts, essentially. We want to look at life on Earth. How did we get here? And we think that that provides important background information to estimate how life would get anywhere in the universe. We're going to talk about where life in the solar system and extrasolar systems, probabilities for such a possibility. Then estimate how common is intelligent life. How should we search for extraterrestrial intelligent species or civilization? And I think it's pretty clear that everyone is probably well aware that there has been this unfortunate silence. And what does this silence suggest scientifically and philosophically? And then we're going to look very briefly at the future. What does it hold in this endeavor? So when we speak about life on Earth, we need to understand how life arose on Earth to be able to estimate how common it might be elsewhere. And here's the first major caveat. We need to admit our ignorance. We are not aware of all the factors required for life. To be able to estimate a probability for our existence, let alone any existence of any other intelligent species, we need to admit that we are ignorant of all the factors for our own existence, let alone anyone else's, okay? So our ideas and our search strategies will clearly be biased. But what else can we do? We have a single example of the technologically intelligent civilization, that is us, the Western civilization since 1950, and we have to really lift ourselves up by our bootstraps to, in fact, understand the factors that we think are important for estimating the intelligent probability for intelligent species elsewhere. So we now look into basic astronomy. A number of these slides are, I think, very, very interesting just in general. I think most of us are aware that our solar system formed about just over 4.5 billion years ago, billion giga and a atom, so billion years ago. The process took about 30 million years. And if we look at this montage really of a sketch of how we think things went, essentially, though the universe is about 13.8 billion years old, there are still a great deal of molecular clouds, even giant molecular clouds, or even smaller gas and dust concentrations in our own galaxy, and we presume many other spiral galaxies and dwarf galaxies in the universe. And it turns out, for some reason, about 4.5 to 5 billion years ago, perhaps because of a nearby supernova that in fact compressed or at least perturbed this happily existing cloud. After all, it had been there for many billions of years since the formation of the universe and our galaxy. It stimulated it, it perturbed it so that, in fact, at least a portion of it compressed and started to collapse under its own gravity. These clouds, or at least the cores of these clouds, are very, very cold and can maintain its size due to internal pressures against this gravity that is trying always to compress it. And it just lost out because of this perturbation. By the way, that supernova also impressed upon our solar system various isotopic abundance ratios, meaning the elements, certain isotopes of certain elements, betray a particular supernova that likely contaminated our molecular cloud from which the solar system formed. After several million years, maybe tens of million years, that gravitational collapse ended up being a pancake type shape because of the conservation of angular momentum, where in fact an ice skater, when she has her arms, she's twirling on the ice far out, she's rotating very slowly, and as she brings her arms in, she rotates more rapidly. That's a law of physics, the conservation of angular momentum. And so you soon get a pancake-shaped distribution here, hotter in the center and cooler towards the edges. And eventually, mass inflows to the center because of the gravity of the dense center, and it gets hotter and ultimately forms a protostar and becomes a bona fide star when nuclear fusion initiates in its very core. So it has to retain temperatures of about 15 million Kelvin for that to happen. Meanwhile, in the outer nebular envelope here, we have the accretion of dust initially onto, pebble-sized objects, accreting onto boulder-sized objects, accreting with time to continent-sized objects, and ultimately to planet-sized objects. And eventually, when the sun became a bona fide star, and the outer planets, particularly the Jovian planets, migrated to the positions they currently have, the inner solar system was cleaned out very rapidly of the gas and dust by solar radiation, and the gravity from the Jovian planets got rid of all the loose materials except for that in the asteroid belt and the Kuiper belt in the outer inner solar system. And much of this was pushed out into, of course, the Oort cloud. And we see here that after about 30 million years, we come to the actually formation of the solar system as we know it. So it's a very short time scale the formation of our solar system occurred. Now, life arose rapidly on Earth. So within the first billion years, there is very good evidence that single-celled life rose rapidly on Earth, and this is a very, very important point. We have stromatolites from Greenland discovered very recently, these are fossilized green algae or cyanobacteria that in fact were, of course, fossilized, so the organic material was replaced by mineralized material, but we still have their shape, and we can age date these minerals. And the oldest stromatolites material from Greenland is over 3.7 billion years old. So less than 1 billion years after Earth's formation, we have clear evidence for the formation of organic material from single-celled algae, or cyanobacteria, as it's more properly called. This is one of the best diagrams that I have ever seen, and I'm pleased that I'm able to show this here because this really is important in this context. This really shows the important stages of life, the development, the evolution of life on Earth on a timeline. So the formation of Earth about 4.56 billion years ago, and that's not, by the way, an age that's dated from a material found on Earth, but rather from the oldest meteorites. So material from the oldest meteorites, from radio dating of uranium to lead, are unambiguously lead us to a lower limit for the age of the solar system, 4.56 billion years ago. And this is very consistent with the stellar evolution models independently that show the sun's age should be very, very similar to this, at least 4.5 billion years. Now, Earth, very soon thereafter, chemically differentiated. The heat due to accretion of these planetesimals eventually to formation of the planet Earth, and radioactive decay in the first billion years led to essentially a remelting of Earth and chemical differentiation, meaning that the most dense materials settled in the core and the least dense materials, the scum, as it were, floated to the crust. The moon, interestingly enough, as you're probably well aware, formed 50 or so million years after this, likely the result of a Mars-sized object that found itself formed closer to Mars, actually, in the outer solar system, collided with Earth, and that material soon kicked out material, and eventually much of that was formed into what we now know as Earth's moon. Now, the oldest the oldest rocks, the oldest materials we have evidence for on Earth are zircons, so crystals that are really, really good at protecting the material inside. So in the Jack Hills range, which is on the very northwestern part of Australia, the continent of Australia, and the Jack Hills zircons date from about 4.4 billion years ago, so less than about a billion, 100 million or so years after Earth's formation, we have evidence for crustal material being formed. So these zircons are not in the original rocks, but zircons are such good containers, essentially, and prevent contamination inside the crystal that we can age date these very precisely. There are other interesting milestones on the way to essentially about 2.7 billion years ago. We have eukaryotic cells, so cells with a nucleus developing. We had a lot of these sediments that I mentioned from Greenland, they do show that there's evidence for organic materials and single-celled creatures as far back as 3.7, 3.8 billion years ago. The rise of atmospheric oxygen, which led, of course, ultimately to the Cambrian explosion a few 100 million years ago, really set the ball rolling for the great diversity of life as we now know it. The dinosaurs on the scale, very, very recent developments, as of course are human beings, less than primates about 50 million years ago. So what do we have here in summary? So the most incredible and most the step about which we're most ignorant is the abiogenesis step, life from non-life. We know it occurred more than 4 billion years ago. Liquid water is required, carbon chemistry is required, and sources of energy. They were all present in the early Earth environment, as I say, more than 4 billion years ago. The eukaryotes, the cells with nuclei, and plants emerged about 2.7 billion years. Bacteria that produced the oxygen that soon took over Earth's atmosphere 2.3 billion years ago, and eventually in the Cambrian explosion, complex life. Primates about 50 million years ago, and we, our species, Homo sapiens, between 200,000 and 300,000 years ago, we imagine. Now, just a point about evolution, it operates through natural selection, and we have the father of the theory of evolution, Darwin here, Charles Darwin, and that's a theory that suggests that genetic variation in a population with mutations are key. That is, some of these mutations, most will be, will not confer an advantage, but with environments changing, some will offer an advantage and will survive preferentially. And we think that intelligence can confer survival advantages. There are some questions about that statement, but in fact, it's generally held that intelligence can confer survival advantages and so will be selected for. It's important to realize that evolution has no goal or purpose as well. So what about life in the solar and extrasolar systems? Well, if we take a look at Mars, and you may be well aware of this, that Mars had a much denser atmosphere in the first billion years, higher temperatures that permitted liquid water on its surface, in other words, between 0 and 100 Celsius. And many models have shown, or at least have suggested, that if there were not large above ground oceans on Mars, it may not have enveloped the whole planet, but there's excellent evidence that there were large bodies of water in the first billion years on Mars, and therefore the conditions were right for the evolution of life, if in fact we were typical on Earth. And there's good evidence for liquid water now on the most interesting Galilean moon in this context, Europa. There's suggestions, and more than suggestions, because both NASA and ESA, the European Space Agency, are very interested in planning for a mission to Europa that would drill down through its surface a few kilometers of ice and then into a subsurface ocean of salt water that may harbor simple life. We see other evidences, of course, for this, Saturnian moons, Enceladus. Anyway, there are situations in the solar system as such that could harbor simple life forms, but certainly not intelligent life. Now, if we in fact look at what's called the habitable zone, this is a very important concept that will allow us to understand where to look in extrasolar systems for possible sites for intelligent life. So, in fact, the habitable zone is simply the region about a star, which is three-dimensional actually, but because planets are in a plane, we talk about an annulus in the planetary disk that would allow temperatures between 0 and 100 degrees Celsius. And if you take a look, this is called the habitable zone. And if you take a look at this habitable zone as a function of stellar type, essentially, here's the sun at 1 solar mass, here's a half a solar mass star or red dwarf, and here's a 2 solar mass star. And these are the planets as they would be in our solar system in fact, a logarithmic radius, or at least a scale which is not linear. And you see this swath here, this is the zone, the habitable zone, where you would search for planets that in fact have liquid water on its surface, which is a crucial factor, a key factor for the development and maintenance of life, both simple and complex. Okay, so now the habitable zone is a very important concept, but we think, based on our example, that evolution would require billions of years to develop intelligent life. It's taken a few billion years in our situation, so it likely will take billions of years in a general or typical situation. So these represent the spectral classes of all the stars, from O stars, the hottest and most massive on the main sequence, through to G stars, like our own sun, and through the red dwarfs, the M stars, which are only a few tenths the mass of the sun. And it turns out that if you take a look at this table and take a look at the spectral class, this gives roughly the mass compared to the sun's mass of each of these different groups. But here's their lifetime in billions of years. How long did they live on the main sequence in a stable situation? And we see that for the majority of stars hotter than the sun, their lifetimes are insufficient to allow for evolution to take place. That is, if it takes billions of years. You would have to look for GK and M stars, or planets around GK and M stars, in fact, to expect evolutionary timescales of billions of years, and therefore possibly to look for sites where intelligent species would or could develop. Now, there are so many conditions that must be, we think, in place to have evolution for intelligent life. Planets must have, of course, not just be in the habitable zone, they need to have a stable atmosphere, and they need to have plate tectonics for climate regulation. It turns out that one of the most important concepts that we still do not fully understand, but we certainly appreciate it, and especially our students appreciate it after we're done with it in the classroom, is the concept of the carbon cycle, which is really a thermostat for climate regulation. And this is, of course, a very topical and important issue when it comes to climate change and global warming. Essentially, in order to have the carbon cycle function, essentially, you can start anywhere along this cycle. So we'll start in the atmosphere where there is carbon dioxide. With rain, it turns out that some of the carbon dioxide, of course, finds its way into the ocean. The ocean, and of course, the creatures in the ocean, a lot of this carbon is sequestered at the bottom of the ocean here. When plates subduct under one another, one plate runs into another and one goes under another. In fact, this carbon, heads underground, and then we have the emergence of fossil fuels, volcanism, etc., from which this carbon will then emerge, both naturally through volcanic eruptions and through human fossil fuel emissions, etc., which put the carbon back in the atmosphere. Now, it turns out that each of these different parts of the cycle can self-regulate, so it could turn on more faster, more slowly, that kind of thing, so that the temperature of the atmosphere and the surface are regulated well. And so that's where things like plate tectonics, amongst other things, come into play, where, even 3 or 4 generations ago, we had no idea that these things were so important. The magnetic field of a planet is very important, as well as it turns out that our own moon is very, very important. The mass of the moon compared to the mass of Earth being over 1% is able to keep Earth's axial tilt just right, so we have seasons that will allow us to have liquid water on its surface for the duration of our planet thus far. So part 3, are they out there? Okay, well, we're going to now play a little game of probability, and I'm going to take you on a diversion that I also take some of my first year classes, although in a different context. So we want to estimate the likelihood of extraterrestrial intelligence in our own galaxy, the Milky Way, which has about a couple 100 billion stars, as you're well aware. And if we're looking, which we can't, but if we were looking from a distance, we would see our galaxy as a spiral galaxy, and even though this is a Andromeda galaxy, we would be sitting out at about here, about 25,000 light years from its center. Okay, so that's what we want to investigate ultimately, but I'm going to ask the question of you. I'd like you to think about how you might estimate how many female, left-handed, naturally red-headed employees work for Air Canada. Now, I know we're at a time where, this is a sensitive issue, but this is only a probability estimate, and we sure hope that we are all back to work again, healthy, and back to work again before the end of this calendar year. But nonetheless, let's do this thought experiment. And how do we approach an experiment like this? You may have heard about Enrico Fermi used to torment his students with questions like, how many barbers are there in Chicago? And you had to estimate that just on the basis of this kind of probability estimate. So how we might do this is, I had to look this up, so I admit this was not off the top of my head, the total number of employees in Air Canada, and they turned out to be just over 40,000. Now, what fraction is female? Turns out that I estimate about 40%, 50%, 30%, 60%, whatever. We're not, the spirit of this is to get a reasonable estimate. What fraction of those is left-handed? It turns out that about 10% of people, in fact, males and females, are left-handed typically. And then what fraction of the population is red-headed? Now, it would make a big difference if we were in Dublin, Ireland, or Reykjavik, but we're in Canada, and the population in general is about 2%. So how do we get then the number of female left-handed, naturally red-headed employees in the end? Well, they're all statistically independent, so we just multiply each of these factors together, and we get about 30, 40 employees. Now, I don't know what the real answer is, but it's probably of that order. Okay, so now let's apply that same thinking to how the Drake equation, named after Frank Drake, who in about 1959, 1960, appreciated that this was a helpful way of estimating probabilities of an extraterrestrial intelligent civilization in our galaxy. And so what we're going to do is a little bit of sleight of hand here. We're going to say technologically intelligent civilizations, and I'll tell you why in a minute. So how to estimate that based on what we did with Air Canada, the number of stars forming in our galaxy each year, times the fraction of stars that have planetary systems, times the number of planets in each system that are in a habitable zone. These three are in a different font color, and they betray the fact that we probably know these pretty well, much, much better than a factor of 10. And then we come to the most uncertain factors. What fraction of these planets will life develop on? What fraction of those planets on which life develops develop intelligent life? What fraction of these then develop communications, interstellar communications? And finally, how long does this communication phase last for technologically intelligent civilization? Well, as I mentioned, we have a good idea of the first few factors. And we have pretty good idea that the extrasolar systems with Earth-like planets in the habitable zone may be commonplace. Satellites like, of course, Kepler and TESS are going to be able to have already, and will be able to really hone in on this particular, these particular factors to exquisite precision in the next generation. But as you know, we even have in our nearest star system, other than our sun, already evidence for planets, Proxima Centauri b, for example. Where the difficulty lies is estimating the biological and sociological complexities. The last few factors are overwhelming, but this doesn't prevent us from making educated guesses. And when you make these educated guesses, you get numbers. Now, this is intelligent civilizations in our galaxy between sub 1, which is, of course, a bit unusual, but you know, that's what the math shows, and to hundreds to thousands and even tens of thousands. We call those, you know, pessimists on the very low side and optimists on the very high side. Folks in the 60s and 70s often got very high values of thousands and tens of thousands of intelligent civilizations currently in our galaxy. Now, there was actually a political motivation for some of those optimistic suggestions. And I'll share with you later why this was the case. But in fact, I think you can guess that in order to communicate or listen to or communicate with extraterrestrial intelligent civilizations, you need the benefit of very large radio telescopes and arrays. And a lot of these optimists were also pressing, particularly in the United States Congress, to build larger and larger radio telescopes in the 60s and 70s. And so there are political motivations to some of these estimates. Now, scientists often invoke what's called the Copernican Principle to justify these large numbers. And that Copernican Principle is, well, you know, Earth's location is not privileged in any way. And we've seen that in a number of occasions throughout scientific revolution, and even in the early part of the 20th century, when we were still trying to put together whether we lived in a single galaxy or all those little nebula in smudgy nebula in the universe, in fact, were their own island universes. So the Copernican Principle is very, very important, but in fact, is it mistakenly, is it inappropriate to invoke the Copernican Principle here because we are so ignorant of all the factors which go into estimating the probability for intelligent life? I think we are, but it's a way of hiding our ignorance, and you know, there's no other way to proceed, so let's move on. So how should we search? We have estimates between 1 and thousands of technologically intelligent civilizations in our galaxy. So how do we search for them? Because to our knowledge, if UFOs don't provide good evidence, we haven't the evidence yet. So we could physically, of course, travel and explore our own galaxy, but the distances and timescales are too large, and current technologies really don't allow us to do this. It's estimated that in about 2 or 3 centuries, we will be able to achieve, through rocket technology development, speeds of maybe 1% the speed of light, which is all you really require to, if you have a coordinated approach, to in fact explore the entire galaxy over a few 100 million years, a long time scale indeed, but in fact well within the age of the universe, the age of the galaxy. So take your mother's advice and listen. So that's how most scientists plan on investigating this critical question. So we could listen for evidence of an extraterrestrial intelligent civilization. And it turns out, for many, many reasons, we would look in the radio frequencies. It turns out that the interstellar and intergalactic media are just opaque to many forms of radiation, gamma rays, X-rays, UV light, and even infrared radiation. Much of the interstellar medium is opaque to this, and so if you sent a particular signal, it would soon get scattered or absorbed. But radio radiation in the gigahertz frequency range is not absorbed or scattered by interstellar and intergalactic material, and so is likely a good frequency or frequency band in which to search or send signals. Now, this is a very interesting diagram, and it has the frequency of your electromagnetic radiation or radio radiation down here, and how strong this radiation is in nature. Okay, so let's take a look at this. So this particular dashed line is in fact the background noise from our own galaxy in the radio regime. This particular black line here shows the cosmic microwave background radiation, which sets, of course, a limit to how faint we can search or hear signals in these frequencies. And this dotted line here represents the noise from our own atmosphere. And so this blue line shows the sum of all of these three components. And it's the lowest value is the least noisy part of the electromagnetic spectrum. And we would anticipate, for a number of reasons, that any signal, either sent or received, should be in this frequency regime. And moreover, in this particular range here of between 1 and 2 gigahertz, there's a lot of water vapor and hydroxyl molecule that nature itself produces frequencies at these frequencies. And so any kind of astronomical savvy intelligent civilization would know that this would be a dead giveaway. A signal in this range would be a dead giveaway that either they in sending or we in receiving is from an intelligent civilization. Okay, so this so-called water hole between 1 and 10 gigahertz at radio frequencies is the preferred window. But that still leaves a huge number of observations to be made over the sky, and this is why progress has been so slow. There have been a number of systematic searches over the past generation, including from Arecibo, which is the second largest single-dish radio telescope in the world, but famous for its searches all the way from 1960s and Frank Drake's experiments, all the way to the SETI Institute, Search for Extraterrestrial Intelligence Institute, in their Allen telescope array, which just uses many dozens of essentially TV dishes, not more sophisticated than TV dishes, in an array format. So there are vagaries of funding and the operation of these arrays, but let's just say to this point, there's only been silence. So another option is to search physically the habitable zones in our galaxy. And how might we do this in a couple of centuries when we develop the technology, both robotic and computer technology, to make what's called von Neumann machines after this concept's initiator, John van Neumann, a very brilliant Hungarian-American mathematician in the mid part of the 20th century. So a von Neumann machine is a self-replicating robotic craft. So the strategy would be clear. If you had the technology, rocket and computer technology, and you could program one of your von Neumann machines to go off, let's say, to the Alpha Centauri system, and the craft would take it 1/10 the speed of light, 40 years or more to get there, and then it would search for evidence for simple life, intelligent life, whatever, And if it did not find any, it would then land on some kind of terrestrial body or an asteroid or something, and then replicate itself with new computer controls to go in search in another particular direction. In fact, you'd build two. For every von Neumann machine, you would build two copies of yourself, send them off to stars that have yet been explored. And you can see in a geometric type series, you could anticipate with very clever algorithms, you could search the whole galaxy for signs of simple and complex life in much, much less than 1 billion years. I know that's a long time for humans, but it's still theoretically possible. So why has there been radio silence? Why no evidence for von Neumann machines from an extraterrestrial intelligence? Well, it turns out that we have, this is just an articulation or enunciation of what Enrico Fermi coined the so-called Fermi Paradox. His question, when asked one day at a lunch around 1950-ish, well, if ETI is ubiquitous, then where are they? Well, again, we have heard only silence, definite silence thus far. So what are the options? Well, let's say we are alone. Okay, that is a possibility to explain the silence, but this is highly unlikely because the sun, being only 4.5 billion years old, is much, much younger than, well, it's much younger than about half the stars in our own Milky Way galaxy. So there are a number of stars with terrestrial-like planets that are older than ours, and even if evolution was really quick here compared to other stars, give it a couple of extra billion years, surely one of those stars on one of the planets around those stars should have, in fact, evolved intelligent life. So this, again, is under the assumption that what transpired here on Earth is typical, including evolutionary timescales. Second option is we are not alone. So, and I think you could probably, you're already thinking in your head, what are some of the options? Well, we're looking at the wrong frequencies. Maybe banging black holes together is the right way of signaling another extraterrestrial intelligent species. Possibly. Perhaps we're the most technologically advanced species in the galaxy, but again, you know, there are many stars, half the stars in our galaxy are older than we are, and one would anticipate that even if evolution, you know, took a little bit longer, they'd still develop complex or intelligent life. Maybe ETIs are monitoring us undetected. So this is like what anthropologists do when they come against or come up with against Stone Age tribes. They view them for a distance, and this is called the Sentinel hypothesis. Maybe the ETIs will leave us alone until we reach a certain level of technology and then communicate with us, because why bother until then? This is called the zoo hypothesis. Maybe an advanced ETI destroys any competition. This is called the predator or super predator hypothesis. So, so this is this is what Stephen Hawking was very concerned with the last few years of his life. He wrote extensively on this issue, and he said, you know, I don't recommend sending signals out willy-nilly in the universe, because it could well be signal our existence to a super predator hypothesis which does not want to be second fiddle to anyone. Or we could live in a simulated universe a la Matrix, but and anyway, I'm not a big fan of that one, but could be. And I mentioned at the very outset that I was going to introduce just this one slide, which is the result of a paper that came out in the last year from the Future of Humanity Institute at Oxford University. And it turns out that this institute, which is a formidable institute with experts in virtually every area that has to do with the future of humankind or humanity, and they looked in exquisite detail and they looked at the probabilities and the uncertainties for each of the different factors in the Drake equation. And when all is said and done, here are their two big, summary statements. That if you treat the Drake equation right with the proper uncertainties, there is a substantial probability that we are alone in our own galaxy, 53 to 99.6%, and perhaps even in the observable universe, between about 40 and 85%. So where are they if they exist? They're probably extremely far away and quite possibly beyond the cosmological horizon and forever unreachable. So this is a profound statement that, we may be alone in our galaxy, so it's not surprising this great silence the great silence is not surprising. And that, in fact, if you really do the math right, we may even be alone in the observable universe. Again, the observable universe meaning, because the universe is only 13.8 billion years old, we can only see out, or light has only a certain amount of time to reach us. The universe could be infinite in fact size, but because the universe is relatively young and not infinitely old, we can only see a certain fraction of that. And it turns out that this horizon is actually increasing faster than, the universe is expanding due to dark energy faster than our horizon, our observational horizon is expanding, and so they will be forever unreachable. Okay, so the last couple of moments, we want to just anticipate what then is there to do in the search for extraterrestrial intelligence in our universe. Well, the SETI Institute, the private institute in California, would recommend, and I think rightly so, that we keep looking. Look, as long as we are just listening, this is not an incredibly expensive prospect. Keep looking and keep sharpening our tools, our detectors, and who knows? If we don't look, we'll never find. Should we ourselves broadcast? Well, again, I mentioned this in the context of the super predator civilization question. Stephen Hawking was deeply concerned that we not betray our position in our own galaxy for fear of a super predator. And who's to say that an ETI will necessarily be good? Is that clear from first principles? It's not at all clear to me, and it's not at all clear, apparently, to a number of philosophers and theologians and others who study these questions. So I find that very, very interesting. Now, what if we do make contact? If we do make contact, there actually, maybe unsurprisingly, is a UN detection policy or protocol. And the first thing that must be done is the signal, extraterrestrial intelligence signal, must be verified. News should then be released to the world. No single state should reply, however, and any response should represent a consensus of states. If we discover an ETI, there's a vast literature that talks about the profound and potential changes that would be in virtually every aspect of life, in science, certainly in technology, in politics, in philosophy, in religion, ... There's not an area of human endeavor that wouldn't be changed. And in fact, one of Frank Drake's books, early books that he wrote on this, he really hoped for ETI communications so that we could become virtually immortal ourselves. That is, we wouldn't succumb to cancers or Alzheimer's diseases, all kinds of other things, neurological diseases, and perhaps even live forever. So what to do? Well, it's a very interesting topic, as I'm sure you'll agree. There's always more to do. There are developments in every facet of, as I say, human investigation that will allow us to sharpen our tools to approach this question even more and more finely. But we need to carry on as astronomers have always carried on. And this is my advice as I bring up my last slide. We should keep looking up, because that is the secret of life, the secret of everyone in the Toronto Centre of the Royal Astronomical Society, and it's good advice in this topic as well. So I leave you there with my talk, I guess it was, and I'm happy to entertain any questions that people may have.
Thank you very much, Michael. Lots and lots to think about. And I'm sure there are many, many folks who are out there on the various YouTube channels who would like to pass along some questions for you. So without any further ado, let me pass it across to our reader of the words, reader of the questions.
All right. Thank you, Paul. Thank you, Professor Robertis. This is Blake Nancaro. I've been monitoring the chat channel, and there were a couple of questions, and I have one as well. Louis asked, what do you think of the late Jacques Monod's view that we are it?
There have been a number of very impressive intellects who have really thought long and hard about the situation and have come to the conclusion that we are alone. And people have done that, my understanding, from a variety of perspectives, from a philosophical perspective, from a theological perspective. I mean, if you take a look at the vast majority of time in the past 2,000 years has been a time where religion played an important role, particularly in the Western world. The Judeo-Christian religion played an important role in the development of society. And if you take a look at the very interesting thoughts that people have had, particularly with respect to the death and resurrection of Jesus. I mean, would another intelligent civilization have had to have their Jesus come, live, and be crucified, died, and rose again for that civilization, in fact, to be redeemed? So very interesting from, let's say, a theological perspective, very interesting directions from a philosophical perspective as well. There are a number of folks from the 70s and 80s, Frank Tipler, for example, Michael Hart, and these folks used scientific arguments that concluded, or at least suggested, that we likely are alone, and they do use interesting pieces of evidence. Let me divert just a second just to share with you a little bit more of this political story about the value for and the number of technologically intelligent civilizations in our galaxy currently. Now, I mentioned that there are a number of folks, scientists, well published, that had large values of N, and it turns out that they were strong proponents also of building larger and larger radio telescopes. Now, it turns out that these folks like Michael Hart, and particularly Frank Tipler, they were getting and publishing values that are about unity, we're it in the galaxy. And it turns out there was actually a publishing blackmail, an intentional blackmail, according to historians of science, of preventing folks that were getting N of about 1, so low values for these probability estimates, from publishing in North American journals. These folks had to go and publish in British and European journals at the time because they were literally blacklisted, presumably because of this political game that some radio astronomers at the time were playing. And so I find that very interesting just as a sidebar. But I think, this great silence is a real challenge. And when you read these conference proceedings, and when you read these philosophers and scientists who really side with very large values of N, I think they still in the end are deeply concerned about the great silence, as it's called, and which of the explanations is the more likely. But no matter which explanation you favor, you still feel uncomfortable in the end about it. And yes, it may well be we're not looking in the right frequencies. Yes, it may well be we're not looking at the right objects. But we're trying our best, and still nothing is coming of it. So, but we still have to persevere.
Okay, thank you. Actually, I have a question for you, if I may. I wanted to know if you had any insight as to why the volunteer program or component of SETI has been concluded or shut down.
I know that the only thing I know, and I don't know even for certain, that they've been having serious financial issues in the last decade or so. They rely on private funding almost exclusively, I think, to maintain and develop their Allen array, for example. And since about the early 90s, it turns out, NASA was involved in many of these experiments until about 1992 or early to mid 1990s. And then because of budget cuts at NASA, they did not contribute much more in the way of supporting the, for example, building of detectors, very sophisticated multiplexing detectors to allow a search for many frequencies all at once and many different directions all at once. And so I know that the SETI Institute has had its ups and downs since the mid-90s, but I think they're particularly having a hard time most recently. And I think, in my understanding, is that's a primary reason why they have not been able to, in fact, achieve and continue with their the projects that they were leading the world in. And I should also point out that some SETI projects do get radio telescope time with Arecibo, with the VLA, that kind of thing. But in fact, it's almost exclusively a scientific instrument. And so scientific experiments and scientific observations are carried out. The observations for SETI represent only a tiny, tiny, tiny slice of time on these telescopes. So once you take out the private endeavor from the SETI Institute, you really don't have much on-sky time to, in fact, carry out these explorations.
Okay, thanks. I'm a little sad by it all. I've had my computer contributing to doing research, up to 3 computers at one time, processing data. But I guess it sounds like unless they get some more funding, that's not going to happen for a while.
But it's a wonder. You're absolutely right. I mean, isn't that a wonderful feeling? I mean, I don't do research in this area, as I'm very, very interested. But we all feel like we can use our CPU cycles to help in the search, in this project, which has immense value for humankind psychologically, as well as scientifically, to know that someone else is out there. If you take a look at some of these surveys, so many people see the value in this type of endeavor because of this strong desire to know whether there is someone else out there. Now, it used to be a century or maybe even less ago that religion satisfied that particular yearning. But in fact, now many people with secularization, many people are sort of transferring this type of yearning to search for an extraterrestrial intelligent civilization. I mean, imagine the kinds of discussions we could have. Of course, they'll, if they're separated by thousands of light years, it'll take a while, but I'm sure we'll overcome with technology.
Thank you again. Ron asked, why does the Drake equation use the rate of star production and not absolute number of stars?
It turns out that, by the way, that's a question that the chair of our department always asks people when anyone talks about the Drake equation. And it's essentially a units problem. It turns out that at the last factor in the Drake equation is the length of time that, how long does a civilization, technologically communicative civilization, last? And by the way, but before I answer that, the original question you had, that's often designated capital L for Drake equation aficionados. And L is actually the second least determined, well-determined factor in the Drake equation. And it gives you shivers, right? Because the great silence could very well mean that L is 100 years, not a billion years, not a million years, but hundreds of years only. And if that's the case, isn't that scary that, you know, no civilization, in fact, makes it much past becoming technologically intelligent because maybe of nuclear holocaust, environmental holocaust, whatever. So that's also an issue. Anyway, L is the time span in years, and actually at the first component, it's how many stars are formed per year, and so that cancels out that time. But it turns out, you know, if you this is sort of a back of the envelope type of approach to, and it turns out that once you're well after the formation of the galaxy, that there's basically a constant star formation rate, and this gives you a good approximation to the situation. So that's why it's used for these two reasons. But good eye for noticing that.
Very good. HBR asked the question, could it be possible that the universe is still young, still too young on a cosmic timescale for advanced civilizations? And he supposes maybe we're the first ones. I think you kind of touched upon that earlier, but can you comment some more on that?
Sure. Now that, to me, that is a fascinating idea. Is it possible that even though we're relative newcomers, you know, Sun is a middle-aged star, let's face it. The first stars that with very low metal abundances in it, so largely hydrogen and helium with just a soupçon of heavier elements. I mean, those were formed, you know, 10 to 12 billion years ago. And so we're 5 billion years ago. So we're middle-aged, okay? And half the stars are older than the Sun, half the stars are the Sun's age or younger. So, you know, there's a significant, you know, and some of the stars formed 10 or 12 billion years ago. It may well be that there just were not enough heavy elements, meaning carbon, nitrogen, oxygen, etc., to form a lot of terrestrial planets like our Earth or Mars, etc., on which has a, you know, solid surface on which liquid water can gather, that kind of thing. But certainly lots of, you know, tens of billions of stars at least are older than the Sun, likely have planetary systems with terrestrial-like planets. And well, it could well be that we're the first that, for whatever reason, that evolution is first off the block here. But, you know, we had these other stars and the planetary systems had such a head start. It just seems implausible when you're dealing with tens of billions to 100 billion stars. You know, not one of them did evolution just have, you know, the conditions were just right so that evolution would, you know, get kickstarted there first, and then they would be in advance of our own galaxy. And then we have to bring in technological intelligence and technological development. I often, perhaps inappropriately, but I often talk to my classes about this topic when I ask them to consider what the lead of only 50 or 100 years a lead does technologically to a civilization. And even though this is a military example, if you were to go back and if you were to take, let's say, the best aircraft carriers and support Navy that the United States has, plunk it in the middle of the North Atlantic, and then go back in time to 1945 and have everyone of the day come and try, you know, to beat that Navy and that Air Force, and it just wouldn't be the case. They would be decimated. So you know, with even less than 100 years technological advance, it's like night and day. And in terms of the ability to be able to presumably wage a war or engage in interstellar communication or interstellar travel. So once you become technologically intelligent, it you know, it accelerates, it almost exponentially accelerates the possibilities. And once computer scientists in particular, but also physical scientists are estimating that von Neumann machines will be a possibility within 2 centuries. We just lack a little bit of rocket technology and a little bit of computer technology. And then when we achieve these levels in both rockets and computers, we will be able to craft our own von Neumann machines, which could then explore the whole galaxy in under 1 billion years. Now, I know that that's a frightening concept when we talk about billions of years projects. You know, when we're talking about governments that from month to month don't even, the planning is poor even from month to month, let alone year to year. But I can't imagine how you could have a 1 billion year project to explore the whole galaxy, but at least it's theoretically possible. So it could well be we're first off the mark, but you know, there's just the math just shows that it's highly unlikely.
I'm just checking in. Thank you again. I'm just checking in with our crew. What's our timing like? How much time do we have left? Can we take some more questions?
Yeah, we can take a few more.
Okay. Phil Chow asked, what would it take for us to interpret a signal coming in from an intelligent civilization source?
That is, these are all been very interesting questions, and that's another question that I find fascinating. It turns out that, you know, we have, in fact, Frank Drake and others have sent signals, so encoded signals, to a few star systems, mostly as a stunt, let's face it. But stunts are helpful sometimes to raise money and draw attention, you know, to your endeavor. So, and they essentially encode, this is quite a long time ago, but basically a picture of, you know, of our solar system and our third planet and what human beings look like, not unlike, you know, what the Sagans, or at least Carl Sagan and his wife, and during, I think I mispronounced her name, developed, you know, for the Voyager spacecraft, right? They had those images and pictures. So imagine encoding them in electromagnetic radiation, so some digital encoding. Now, if we're going to receive these signals, we're clearly, you know, technologically inferior, if you can use that term, to the senders, right? And so they have to first make it simple enough, make it complicated enough so that we're not confusing the signal with a natural source, a pulsar or whatever. So that's the first thing. So it has to be not natural. It has to be simple enough because we're not that smart on their scale, technologically at least. And so, and it has to be repetitive. You can't just send it once and then expect, you know, all these neophytes to, in fact, detect and interpret the signal. So it has to be repetitive. And so, and some people have thought, some mathematicians and others who are really savvy in this area say, well, you know, one way to make sure that this is not misinterpreted as a natural signal is to make sure you embed a number of universal constants like pi or e, or so make sure, you know, that if someone knows that, you know, you've just sent a code that represents pi or e or gamma or whatever type of thing, that people would, the receivers would immediately know this is from an intelligent species. So there are all kinds of really interesting ways that people have had ideas of how to set up some kind of signal. And on the other hand, you know, to receive the signal, we have to have, if the intention is to let us know that there is someone else out there, keep banging the rocks together, boys, then okay, or boys and girls. So that's one thing, but you've got to make sure it's simple enough to decode. But again, you know, this again betrays, you know, all kinds of anthropocentrism, and we only have our own species, our own ideas, our own technologies to work from. and we only hope that we could, with enough enough grit and intelligence, be able to decode some of these signals. But it's a very interesting question, and there are parts of conferences just devoted to that question, to answer that question, what we might expect, or if we were to send a signal, how we might fashion it.
It's not so much a question, but one of our members, Tom, talked about radio frequency and that it might not be used for a long time. We might not use it beyond, say, the next 50 years. We might have some other technology. So is that another factor? Does the Drake equation consider that there's different ways that the presence of a civilization remotely would be detected? You've talked about doing something with black holes, suggesting a very advanced capability or technology, and with now LIGO and other instruments able to detect things in a new way. Is that a whole sort of undertone of this, that there are other areas where we can look for signal?
Yeah, I really appreciate that question, because surely it's a possibility. We're all excited to, in fact, narrow frequencies down to 1 to 10 gigahertz because, even now, I think most of us are likely inside, surrounded by, quote, four walls. And, if the walls are thick enough, have a little lead in them, you can't communicate using X-rays or ultraviolet light through these walls, or, whatever, even visible light through these walls. But you can, transmit 1 to 10 gigahertz through these walls without a problem. The radiation doesn't even see these walls. So that's the kind of thinking, that led to, most people suggesting that it's almost certainly got to be between 1 and 10 gigahertz in the radio regime. Quite apart from the fact, of course, that it's very inexpensive to send and to broadcast and to receive too. But as you say, who knows? Maybe we'll grow out of this radio phase in 7.5 years, and maybe it'll be when I suggested, not entirely facetiously, about banging two black holes together, the idea of, in fact, sending, gravitational waves. Maybe no one's going to worry about electromagnetic radiation, but, any civilization worth its salt would send messages through gravitational radiation. And of course, that's not electromagnetic radiation. It's not subject, to interstellar extinction or interstellar scattering or attenuation or anything like that, and can be transmitted across the observable universe without a problem. But of course, that's a formidable challenge for us to develop these technologies. But you're absolutely right. Maybe that's how intelligent civilizations communicate. And by the way, just one other thing that I often like to introduce. The Drake equation has its limitations. And one of the limitations the Drake equation has is it doesn't take into consideration a colonization. So presumably in thousands of years, some colonies, Homo sapien colonies, will live elsewhere, live on Mars, live on space stations, whatever, ultimately maybe in other star systems. So once we start, from a home planet on which we evolved, and then we develop all these little nodes, each of us sending, signals to one another, and people could be excused or other civilizations could be excused for thinking there are multiple civilizations involved in this, but actually there was only one with a number of different colonies. So, that kind of challenge is not really taken care of by the plain Drake equation. You have to make some changes to the Drake equation. So it's a lower, it's an upper limit. So the silence is even more deafening once we recognize that colonization is a very real possibility. And even still, we haven't heard anything. So there's still a great silence. But again, it could very well be we're not looking at the right frequencies. Agree 100%.
Okay, thank you very much. That's all the questions that I see in our YouTube chat. So I'll hand it back to you guys. Any closing comments?
Thanks very much, Blake. Well, Michael, you've given us lots to think about. There's been much ground covered, a great deal of space covered, shall we say, not only scientifically, but philosophically. I think we'll all agree that we live in very exciting times, and that over the next few decades, and I hope even shorter than that, we may get some more inkling of an answer. But on behalf of the Toronto Centre of the Royal Astronomical Society of Canada, thank you for your time tonight, for your expertise, and I'm hoping that lots of people tune into this broadcast after the fact. Thank you very much, Michael.
Thank you very much for the opportunity.